I'm honored that you came to listen to me today instead of sleeping in early Monday morning. But we'll dive right in. And yeah, as mentioned, today I'll be chatting a little bit and sharing a bit about my thoughts on deep learning and transformers. So I'm not quite that old, as despite what you may think. But if we take a look a bit in the past, deep learning methods have actually been around for a really, really long time. So even in the 1950s, you had people developing gradient descent methods for data sets and developing the first learning methods based on perceptrons. In the 80s and 90s, you had people developing backprop and the first deep neural networks. But I guess a question I'll really ask rhetorically is why has it really exploded in the last decade and become like something that the New York Times talks about? And so my answer to this is four key reasons. One is the explosion of the amount of data because of the internet. So like back in the day, we had Wikipedia and ImageNet, and now we really have the ability to utilize really uncurated sources of data like YouTube and pretty much all the internet. Second is the ability of hardware that we didn't have before. So this is, for example, specialized chips and even faster GPUs and TPUs and tensor processing units and really, really big optimized data centers to basically leverage and compute on all this amounts of data. Third is, of course, as many of you probably use, easier AutoGrad software in the form of like these deep learning frameworks like JAX and PyTorch and all the accompanying libraries that makes it easy for someone to just like train a neural network in a collab, as you'll do later today. And finally, as I'll argue, the recent invention of really expressive, powerful models like the transformer that effectively, most importantly, effectively utilize the hardware during training. So this enables efficient training over these large data sets. And so all these four components come together for a perfect storm, and that enables like pretty amazing things that we can do today. And so, I mean, I started in this field maybe like a decade ago, and just the progress has been incredible. And so, kind of, I guess, a lot of the deep learning, some people say at least, really kicked off in 2015, 2013-ish, when the ImageNet challenge was started, and you had these networks like AlexNet, and reaching human-level image classification accuracy, at least on this data set. You have a bunch of other milestones that the deep learning community hit, for example, visual reasoning understanding, text understanding, slowly reaching and outperforming humans on a bunch of these isolated benchmarks. And then finally, probably most recently, is I think one of the really awesome achievements that we had in the past year, maybe like a month and a half ago, that we outcompeted a bunch of really talented Olympians at the International Math Olympiad. And so these models can do great math, they can do great coding, as you probably have already used, great visual reasoning, great text understanding. And it's all sort of made possible by deep learning and transformers. And so when I first started computer vision and NLP, there was a lot of talk in the lectures about all these hand engineering features like Haar cascades and histogram gradients and n-grams in NLP and bag of words, and it's really had to memorize all these things and train these and extract kind of like very handcrafted features from these images and raw media. Time to say goodbye to all of that. The whole ethos of deep learning, in my view, is basically to learn all this, throw out those hand engineering features, and learn from the data itself, because the data tells the real story behind everything. And so now that you have sort of a high-level bird's-eye view of everything, I think it might be good to jump into some of the building blocks that you'll use later today. So the sort of key building block of a deep neural network is the perceptron. It's a pretty straightforward little building block. You take your inputs, use your features, your feature values. You have learnable weights that you want to learn from the data. You dot product your input with your weights. You then apply some sort of non-linearity or activation function, and then you get your output. Easy peasy. So put into sort of a bit more formalized, you have your dot product, your linear combination of inputs. You usually add a learnable bias as well. You have a magical nonlinear activation function, and then that yields an output that you will pass on to future perceptrons. Importantly, you want to be able to do this in an efficient manner on hardware. And so oftentimes, you don't just iterate through this in big sum to do the dot product. You represent it as matrix multiplies, because GPUs do matrix multiplies very, very efficiently. And so you do a whole batch of inputs on a whole wide range of inputs simultaneously using matrix multiplies, and then do this exact same operation, a simple add and nonlinearity. So let's chat a bit about activation functions, or this nonlinearity. So without this, all we'd be learning is linear functions, which can't really represent that much, and you can't really do much with linear functions. But when you add this nonlinearities into the networks, you have this suddenly magical ability to represent sort of any function, any continuous function that you want, given a large enough, wide enough, one-layer MLP. There is a whole wide range of ice cream flavors here that you can choose for your nonlinearities. Back in the days, you used to use things like RailUs and leaky RailUs, and I remember when exponential LUs came out too. Those were in vogue for a while, and TANH as well. A lot of basic machine learning courses cover. These days, in modern transformers, you use something called a swig-glue, which has a lot of nice properties, and a lot of research has gone into. It has properties like it's smooth, differentiable, non-monotonic, so it allows really nice gradient flow backwards, and probably most importantly, it's compute efficient compared to a lot of other and compute efficient on GPU hardware that a lot of other activation functions are not. I should say, if anyone had any questions, you can. I know it's a big room, but you can feel free to raise your hand, and don't be shy. So now we have our basically our core unit building block of a perceptron. Now let's start piecing together slowly up the stack. So when we add if we put a bunch of perceptrons side by side, then you get something called a dense layer, which basically all inputs are densely connected to each of the outputs. And so you just have a bunch of perceptrons essentially side by side, processing all the inputs simultaneously. And then you stack it even further, so that's stacking in width. And then now you do the same exact computation again, and then you can stack in depth as well. And so this suddenly becomes a very, very expressive model that can really represent any sort of function that you want to use to model your data. And importantly, what we're actually trying to do is, again, learn these learnable weight parameters. And so now, okay, great. So now what do we have? We have this network, or this layering of perceptrons that take in some input, process them using the weight matrices that I mentioned, these learnable parameters. Then we get some output. Great. And so then that gets us some output, but that output at the start of our model is probably, start of our training process, is probably pretty bad. It doesn't actually learn anything. It doesn't actually, the function actually just produces random outputs. Then how do we make it so that the model actually does what we want it to do? And so this is where our magical loss function comes in. So basically, when I say loss, it's basically the cost incurred by incorrect predictions of the model. And we measure the loss when we actually train these models. We measure the loss over the entire data set. And so this is, I guess, what you can call the empirical loss. And there's a lot of different formulation. It's also known as, I guess, in other textbooks, you have like objective function, cost function, empirical risk. There's a bajillion names for what is a pretty simple concept. But yeah, and so basically it's a way of comparing your ground truth labels that you have in your data set with their model predictions and seeing how well they align or not. And based on that, using that as your training reward signal. And so, as many of you know, if you go to like the Torch NN libraries, there's like a bajillion loss functions that you can choose from. L1, basically just the L1 error between your ground truth and your predictions, your mean squared error losses, binary cross entropy for classification losses, and all these sort of fun loss functions that you can choose among based on like what sort of task you have, whether it's a regression or classification task, whether you have labels available or not, and your desired learning characteristics of the specific problem that you want to model. And so great. So now we have an idea of how we want to, how to judge whether a network is good or not, and find how to get a learning signal. And now we actually want to make the model good. And so by make the model good, I mean find basically a weight set that makes the model produce accurate predictions. And it minimizes, importantly, minimizes the loss function that we chose. And so for very deep and very wide networks, this is actually a very tricky optimization problem because we are optimizing nowadays billions of parameters, billions of different little variables that we can toggle. And so in my small example here of the loss curve, I only have 2 weights, like that'd be like a two wide MLP. But you can imagine this graph with billions of axes, and we're trying to optimize over that entire surface, which is a very, very complex task. And so the question is, how do we actually go about finding that magical set of weights that yields the minima on this extremely high dimensional loss curve? And so we use this magic algorithm called gradient descent, which makes all of deep learning possible now. So first, in a nutshell, you have four steps in gradient descent. First, you randomly pick a W, or an initialization of all those weight variables, hoping that it does something good. And then you start traversing the loss surface step by step. And so you have the explicit analytic formulation for your network, and so you can compute the gradient or the derivative, the multivariable derivative of that loss function and your network. And so you can compute the gradient, and that gives you the direction of decreasing loss on this loss curve, on this huge loss surface. And you take a small step in the direction that the gradient tells you to go. And so here, like for example, you might initialize your weights at this point in the loss surface based on what you chose as your W0 and W1. You take a small step, and then you keep on computing the gradient and taking small step after small step. And you just repeat this until ideally you reach convergence. Convergence in your loss function is the loss function flattens out, or more realistically, you run out of compute hours on your GCP instance or something. And so written differently and maybe a bit more what you see in a textbook, you initialize your weights randomly. For example, here we're sampling from a normal distribution. And this is actually, I think, a very underrated part of neural network training. Good initialization can make or break you. Then you start looping with some sort of stop condition, whether it's you get tired and you're tired of waiting for your network to train, or you until your loss converges. You compute your gradients analytically and then you update your weights based on the gradient that you have. So one thing I'd like to point out is this magical little parameter that is a talk of the town, which is the learning rate, or the size of each gradient step. And this is notoriously hard to tune, as maybe many of you know. There's a lot of ways you can tune this, whether it's just loads of compute, you can sweep over lots of learning rates, you can do more sophisticated methods. And this is, I guess, one of the the difficulty of tuning this is one of the things that differentiate a lot of different optimizers that you can choose among. So I previously described vanilla stochastic gradient descent. That, yes, is basically the bread and butter of deep learning. But modern optimizers play with a lot of different characteristics of the optimization process. So for example, you can tune the learning rate adaptively during the course of training based on the learning dynamics. There's also modern optimizers like Atom deal a lot with tracking the momentum of these updates, and basically how the gradients change over time, so that it doesn't isn't negatively impacted by like a single bad batch of data. And also, quite importantly, and as you'll see as a common theme in the talk, memory efficiency is very important also for these optimizers, because oftentimes you're constrained by what you can fit in your GPU. And so we often prefer optimizers that don't require really big buffers to store your momentum matrices and things like this. And I should note that, as you might use in your lab today, I suspect at least, you will probably use, is very commonly used, this Atom W optimizer that's pretty much like all open source LLMs use these days. And the final, so if you go to like the Torch optimization libraries, you might find like a dozen different optimizers you can choose from. And similarly, as I mentioned, you have this magical learning rate parameter to control your step size. You can adjust that over time, and you can have a schedule for that learning rate parameter, and that the Torch optimization libraries have pre-built schedules for these learning rates as well over the course of training. Great, and so like when you take a step back, we've covered perceptrons, we've covered stacking them to create slightly more deeper networks, we've covered the bit of the losses, and we covered how to optimize them. So taking a step back, let's put it all together. So we have our model, which is our stack of perceptrons. We also, quite underrated, is actually taking a look at your data. And so in this picture of the cat, you might feed that to a model represented as like RGB values. You feed it into the model, you get your predictions, which might be, for example, a vector of basically a vector representing the logits or probabilities of each of the categories of classification. You compute a loss function based on the ground truth. For example, in here might be some sort of cross-entropy loss. And then you start optimizing it and slowly tuning your model parameters in the optimization process to get better and better prediction probabilities. This is what you might see in a textbook. And when you actually take a look at modern day training pipelines, it's actually quite different, in my opinion. And so there's a lot of people, I guess, this is a simple supervised classification problem. And in modern day LLMs, if you read, for example, the Llama paper or the DeepSeek papers, there's like a bajillion different training steps that we probably won't have time to cover, but I'm happy to answer any questions. So first, oftentimes in very big networks, you have a self-supervised pre-training step. So basically trying to learn from without labels using, like, for example, alignment between image and text, or you might have self-consistency losses or self-prediction losses, like, for example, next token prediction losses, or consistency across different augmentations. So long story short, you basically have a pre-training phase where you use losses that don't use labels. Then you get into your basically main bulk of your training, which is sort of what I described. Then you have like almost like the post-training techniques, which is, for example, if my cat, for efficiency reasons, I might have input data that's only 256 by 256, but when you upload things online, you want your Geminis or ChatGPTs to be able to handle 4K images, and so you gradually adapt the network and train with progressively higher resolutions during training. You train for longer sequence lengths as a different stage of training, and as is very in fashion in vogue these days, you start fine-tuning on human preference data and doing a lot of RL post-training and learning, basically getting your reward signal or your learning signal either in a supervised or RL fashion from very curated amounts of data from human preference and human interaction data, or you get this learning signal from coding environments or execution environments. Great. So I'll actually take a small breather here. If anyone has any questions, I think we have, that was kind of a lot in a very short amount of time. Yes. Yeah. Yes. Yeah, so I guess it's maybe less self-supervised, but more. Yes, sorry. So the question is, basically, I skimmed over in a single bullet point, the chat about like image text alignment as this multimodal alignment bullet point. And my understanding, and correct me if I'm wrong, the question is like, how is this self-supervised learning, and to describe it in a bit more detail. So I guess maybe this is like a misclassification. It might be more weakly supervised, might be classified, this multimodal alignment might be classified a bit as like weakly supervised learning. So in what I'm referring to here is when you actually go out and scrape the web for lots and lots of content, you get these, when you scrape, I don't know, like a website that has images, you get an image, and then if you take a look at the metadata of that image online, you'll get something called alt text, which basically is the website creator or helpful people on their internet basically put a small little description of what that image is about. Oftentimes it's really noisy, doesn't actually describe what the image is about, but basically, the long story short is you get these very helpful pairs. So for example, you get a picture of a cat, and maybe some helpful person on Yahoo Answers put text right beside that cat that's like, my cute little gray tabby cat. And so now you have these pairs of images and corresponding captions or descriptions of the image. And so you have this sort of like training signal that links, okay, when I encode this feature, when I encode this image into a bunch of image features, and I encode this text as the text of like my gray tabby cat, as to create a feature vector representing that text, that my image feature and my text feature should be closer in space than a picture of like the features for the dog. And so maybe I don't quite have the ground truth label of, okay, this is a exact cat of this age, whatever, but I have this like weak supervision that across the text and image modalities, there should be some sort of alignment between the modalities of a single training example. And so it's not quite, I guess, it's more of a semantic difference, but it's not quite supervised, but it's also, I guess, what you would call weakly supervised multimodal training. A very long answer for your very short question. Yes, up there. Yeah. So I think correct me if I'm wrong, the question is, when you actually go on the web is a crazy place, and you shouldn't trust anything on the web. And the image captions are often terrible. And so the specific example that was given is that you have this picture of this cute gray cat, and someone might say, oh, this is actually a Black Panther, because I watched the movie the other day. And yes, this is absolutely correct. Astute observation that in practice you will get this like pretty crappy data, and the question is like, how do we actually correct for this? And the answer is, well, either you make your models and learning algorithm robust to this sort of like crappy data, or realistically you try to correct it somehow, either manually by taking a look at the data yourselves, as you always should, or you have automated corrections of the data. So for example, a lot of works these days use pre-trained models, like for example, older versions of Gemini or ChatGPT to create synthetic captions for your images, and then see how well that aligns with the captions that the internet provides you. And so that way you can see, okay, maybe this caption's like really off, and it's saying this is a picture of a fish, and so you're like, okay, maybe this is a bad, poorly aligned text and image, and so I should either throw this example out or recaption it, something like this. Hopefully it answers your question. Cool. Any other, yes? Yep. Yeah. So the question was, we commonly use swig-glue activations for transformers. The question is whether swig-glue would work for other networks. I think you might need to refer to the actual swig-glue paper for this. They probably have experiments on this. My hunch, and certainly I'm going to tell lots of people online on YouTube the wrong thing, is that it probably is going to be fine if you use this for like your ResNet or whatever. And yeah, so give it a shot. The best thing is to experiment and to eat up your GPU hours. Yes. So the question is about, quote, quote, over-teaching the model and how to protect ourselves from this. I think probably what you might be referring to is this overfitting of the model to the training data. And this often happens if you have a very expressive, very big model and very little data, which you often have in like scientific domains and things like this. The like textbook strategy for avoiding overfitting is you have a small subset of your data that you use as your validation set, and you compare your training loss with the loss on this held out data that you're not training on. And if there's a big divergence between your training loss and the loss that you have on this held out amount of data, this means that you're overfitting to your training loss. And your validation loss is like plateauing and not decreasing as well. But your training loss is also decreasing. While your validation loss is plateauing. And so this divergence between your train and validation loss is one way you can detect if your model is overfitting. I think this is probably the simplest way to detect if your model is overfitting. Any other questions? Cool, excellent. Everything understood, perfect. I did a great job. And so time to dive into the second part of this talk, which is about transformers. And so I guess when I started working in machine learning, we had to take a bunch of classes, in machine learning, as one does, and each of the different classes, about like an RL class, an NLP class, they all had these bespoke architectures and bespoke methods for their specific problems. And for example, like in computer vision, we'd always use CNNs like ResNet and AlexNet and things like this. For NLP, they often used like Markov chains and recurrent networks, and there was a bunch of for other domains, you had these specialized models, and now you have it all easy because now it's all pretty much just transformers all the way down. And so the transformer sort of takeover, I guess you can call it, is like the past half decade to a decade. And now that same slide would be something like this, where it's all basically blocks of transformer layers and attention layers. This is a vast oversimplification, and there's actually like quite a lot of nuance to this, but for the sake of making a flashy presentation, I like this slide. And indeed, when you actually take a look at all these like flagship famous models that you see in the newspapers or whatever, that's driving stock prices and whatever, they're all sort of transformer based, which kind of makes it like hopefully motivates you to pay attention during your LLM lab and pay attention at like 9:45 a.m. today about what this model is. And so I guess the seminal paper people talk about when talking about transformers is this paper called "Attention is All You Need" by this group of researchers that came out in 2017. And the core building block is this attention mechanism, as the paper title suggests. And it's essentially almost like a dictionary lookup in a very, very high level bird's eye view sense. It's a soft dictionary lookup. So what you have is, imagine this scenario where you have a query vector and you want to you first, basically in the attention mechanism, you take this query vector, you dot product it with these other vectors that you have called keys, and then you dot product and then normalize it using this function called a softmax function. And then you dot product q times k, and then you get these scalars out, these attention weights called a, and then you apply this function to normalize that list of attention weights. And then you get this basically vector that represents the similarities between this query q and the corresponding keys. And so basically, how similar is your query with each of these stored keys that you have in the dictionary? And so you get these almost like attention weights, they call it, or you can think of it also as like a normalized similarity values. And then you use those attention weights as basically how to weight the values in the dictionary. So you basically take those attention weights, multiply it by their value vectors, and then sum those weighted value vectors across all the values. And so you basically, and so you have basically your query, you get your attention weights by dot product your query and keys. You use those attention weights to take the weighted sum over your values, and their weighted sum over your values is the output of the attention block. And oftentimes, so one big question is, how in the world do you get this query vector? How in the world do you get these key vectors? And how in the world do you get your value vectors in this mechanism? And so this is where the learnable parameters, or the learnable part of the attention matrix, comes in. And so you have basically a matrix, basically a linear learnable layer that takes in your input and then produces these key values. And you have another basically little linear layer, learnable layer, that takes in your input and produces your value vectors. And similarly, you can have your input also produce a learnable small little layer that produces your query vectors too. And whenever basically your query vectors are produced by that same input, you call it self-attention. So basically this x times your learnable weight matrix, query matrix, producing the q, or that query vector can come from a totally different input that they call y in this terminology. And that is what we'll call as like either regular attention or cross attention. Okay. Unfortunately, it's not just that simple. And so in reality, you're doing this many, many times on many, many inputs. And so, and also the design is like slightly more parallelized. And so in particular, you have you're forming multiple queries at the same time. And you're doing this, basically running this attention operation simultaneously as like and you have multiple, you don't just have like one set of query key and value matrices that you're trying to learn. You're trying to learn basically this same operation multiple times and concatenating the output at the end. So this is basically what they call the multi-head attention. Basically running your attention operation on the same exact input multiple times, each with its own learnable set of matrices, and then outputting it multiple times. And the sort of intuition behind this is that for each individual query, you might want to have different attention weights for different queries. So for example, for a particular, let's say, input sentence, you might want to focus on the subject to determine what the output of that answer to that sentence might be. But then also for in that same output sentence, you might want to worry about the conjugation and the actual like verbs and stuff. And so you want a different set of attention patterns that take a look at different parts of the input. And so as such, so people have just empirically found that having multiple parallel instances of the same attention operation in what they call a multi-head way is effective and a more expressive model. And then finally, you do some like length dimensionality, like a small little details is that you do some sort of normalization based on the dimensionality of your keys, and then you run another softmax at the output, and voila, you have your attention mechanism. And kind of importantly, and of like crucial, relevant to a lot of modern day research, is that this operation is scales very poorly with input sequence length. And so in particular, it's quadratic because you're producing this very big attention matrix that is of the order of n squared if n is the length of your input sequence. And this, if you have very, very long, if you, for example, have a context length of like 100,000 tokens that you're trying to put your entire code base into Gemini, then suddenly you need to store this big matrix that's 100,000 by 100,000, and that's going to blow up your GPU memory and make everyone sad. And so, yeah, and so basically, I'll talk a little bit about this later, but yeah, this is like one of the key computational bottlenecks of this attention operation. Yes, so you can do optimizations during inference to avoid reconstructing that entire matrix, but at the same time, yeah, I mean, during inference you'll have a lower memory load. Long story short, and so this is like a sort of a key operation here. So I want to maybe take a time in case there's questions or being unclear. Yep. Yeah, that's a very good point, and I wish I might maybe. We'll do a live demo, apps, segment, anything. And so yes, long story short, you can visualize the actual attention maps of transformer networks, and they're often very instructive to know, like, here's a good one. Okay, we'll avoid that demo. But yeah, you can take a look at the attention maps, and they're often very instructive to know what the model is actually like taking a look at when you have like an input image or like an MRI or something. And so you want to know, like, oh, which part of the brain is it causing it to, like, this brain image, is it causing it to yield a cancer classification or something? And attention maps, visualizing the attention maps or these attention values is like quite useful in interpretability. Cool. And oh yes, yep. Yeah, that's a great question. So the question was, there's a lot of works that basically try to improve this quadratic complexity. For example, what was mentioned in the question is this Linformer paper. And the question is, are they actually used in practice? I'd say most of them are not, for various reasons, as I'll talk about shortly. And there are a lot of methods that are used to address the quadratic complexity, but I'd say a lot are not because they degrade performance. And if you oftentimes you have this, if you're shooting for highest performance and you're having engineering bottlenecks, it's like a lot easier to solve the engineering bottlenecks. If you have you can throw more people and throw more hardware at a problem and get better performance, versus like fundamental modeling challenges that will degrade performance. Any other questions? Cool. So yeah, so great. So now that's the actual attention mechanism. And so now let's actually put together an entire transformer layer using that attention mechanism. And so in the original Attention is All You Need paper, they had this basically encoder-decoder mechanism where the intuition behind the encoder is that you basically read and understand the user's input, like for example, the question, and the decoder actually generates the response, given the features that encode the information from the user's input. And so the first bit of the transformer layer is this input tokenization and embedding. And so first you do a tokenization procedure using a tokenizer, like a subword tokenizer, like byte pair encoding or something. And then this splits up your input into like little chunks, what we call tokens. Those tokens are then mapped to vocabulary numbers, or basically vocabulary indices, that index into basically an embedding layer. And so this basically maps your vocabulary into these d-dimensional vectors. And these vectors are your actual input to your large language model or vision model. And then kind of importantly and kind of interestingly is that if you recall, the attention mechanism actually is just a dot product, fundamentally like uses a dot product of your input with your keys. And so there's no, when you take this sum, there's no idea of like the ordering of your dot product, right? Because it's all, addition is commutative. And so you want to encode the position of each of these vectors, of where it is in the sentence or the token sequence. And so to do this, you have some sort of representation of the position of each of the tokens in the sequence and add it to the mapped d-dimensional vector that the token mapped to. So you take you tokenize, you add in a position embedding representing the position of each of the tokens, and voila, you have your input to your transformer layer. And then next, you do this multi-head self-attention that I talked about. That's the core operation in here. And then after that, you then apply an MLP. It's just exactly what I described before, which is just almost like a perceptron layer with your learnable linear matrix W. Then you apply your nonlinearity, a swigglue, and then another linear matrix multiply. And there's a lot of people that sort of investigated like this sort of interesting like attention operation, then MLP layer, the design of this sort of like architecture. And there's some sort of people that say that this is where a lot of the knowledge is actually stored in like a lot of transformer layers, a lot of the actual learnable layers is in this MLP. And so it's a very important part of the transformer block. And it contains the bulk of the parameters as well in an entire transformer network. And there's some people that say that this is actually where a lot of the knowledge is stored in transformer networks. And yeah, you can also think of it as a one-by-one convolution. And so, great. So we have our input encoding, we have our attention operation, we have our MLP layers on top of that, their attention operation. Next, quite importantly, is you also have a residual network, which improves the gradient flow when you actually learn this network. Basically skipping, you can tell the model, okay, you can just also add it to the original input, the output of this, like output of the MLP, add it to the original input as well. And finally, last but not what you call a skip connection, also called a residual block. And then finally, quite importantly, in another area of research is normalization within transformer networks. And there's sort of like two schools of thought. Previously in the original paper, they used something called a post-norm transformer layer, which is basically applying the layer norm after this entire residual block. And now, oftentimes in like DeepSeek and Gemma and stuff, and other transformer networks, you have a pre-norm transformer block, which is basically applying this normalization before you actually get to before you actually put it into your attention mechanism, or sorry, before you actually put it into the MLP layers. Great. So that was quite a mouthful. And now we actually have a bit of an understanding of what goes into a transformer layer. And now how do we put it all together? So oftentimes you might see like different flavors of transformer networks, especially vision transformers, that of different like prefixed sizes. So oftentimes people stack 6 of these and call it like a VIT small. People stack 12 of these and call it like a large or base transformer. And this basically encodes all your input into a sequence of vectors that represent the input sequence. But notably, this is how you how you process your input sequence, but it doesn't tell you or actually produce your output sequence yet, which might be of a very different length. And so that comes in the decoding phase. And in the decoding phase, basically you take in whatever the encoder produced, and then you want to start producing the output that you desire. So in particular here, Z is whatever like output tokens that you want, and then it's conditioned on whatever is input you're like, for example, the detective investigated, and then you want to complete the sentence, and it's conditioned on the encoding of the context of whatever you put in. And so what then, like the decoder essentially is an auto-regressive model, meaning that you first output one token, and then in the next generation process, you condition on what you already, not only your input context, but also what you already generated, and so on and so forth, that basically you're conditioning your next step of the model on your original encoder input X here, or sorry, your encoder output X here, and then also what you previously generated. So for example, the detective investigated, and you have a token like a space token or whatever, and that will be your Z1, and then you also have another token that's like the cat, and then that'll be your Z2. And so you keep on generating these Z's autoregressively, and each time you generate something new, it's a full pass through your decoder model, so it's very expensive. And yeah, and so you basically keep on generating it, running the decoder model again and again and again to produce each token that you want to have in the output. And then once you have this like set of outputs, what your output is actually just like a set of probability vectors for the probability over your vocabulary, and then you need to search through all these probability vectors to sample a sentence. Basically, what is the most, for example, what is the most likely what is the most likely token for each of the positions in the output sequence, and that's, for example, your greedy sampling across all your probabilities. And there's a lot of other sampling strategies given the output of your transformer decoder that I won't have time to go into. So now I was given a lot of talk about compute efficiency, but you might say, hey, Skanda, like this is a bit weird because you're basically running the model again and again and again, this decoder model, in order to produce a single sentence output, and that's not very efficient. And so during training time, if you do it repeated iterative decoding, that's very, very slow. And so during training time, what we do is this like what they call mass self-attention, to basically run the decoder in parallel multiple times across the entire sequence. So that way you don't need to first produce this beginning of sentence token, then run the model again to get this next bit of token and then the next token. You can actually run the model once and then get all the outputs simultaneously, and your training becomes much, much more efficient when you can generate the entire sentence all at once. And so the way this actually works is through basically masking the attention values. And so in particular, you want basically to simulate running the decoder model on each individual token. So for example, whenever I'm producing in the first step, when I input my beginning of sentence token, I want it to produce this first token, and notably, it should be ignoring all the other bits of the sentences because it doesn't have access to this, and it's only in the first step of the decoding process. And so during the attention matrix should basically zero out all the other values of the sentence during train time, and only the attention matrix should only basically be attending to this first output or the first input, and then this like masked attention matrix for the second to simulate the second step of the iterative decoding should only be taking a look at or paying attention to the tokens previous to it. And so this is basically, for example, we'll only have a mask of 2 ones in the masked attention matrix. And so basically, during training, you basically have this like nice structure of a mask, a triangular matrix that basically enables basically a certain part of the sequence to only take a look at in the attention the tokens that were before it. And so this enables you to basically train over an entire sequence to simulate the iterative decoding process in a single forward pass, long story short. And so that's during training time. During generation time, you don't have this trick because you don't actually have the outputs available to you. So basically still during training time, when you actually go to like Gemini or ChatGPT, it's actually doing the autoregressive decoding. And so that's very slow. And also one way that make it a little bit faster that oftentimes models use is this idea of KV caching, which is basically pre-computing a lot of the keys and values, for example, for your system prompt or whatever, and then applying this slow iterative process now that you have pre-computed your keys and values for part of your sentence or part of your context that you already know up front. Yeah, and so this KV cache is actually quite big oftentimes. So for example, in the Gemma model, this is like about 40 gigabytes of vectors. And there's a lot of research on how to make this more efficient and smaller memory footprint. Great. So in interest of time, I'll jump a little bit and say that, okay, you have the outputs to your decoder. There's some small amount of processing you do at the end in order to get your final output tokens. This attention is all you need paper was like hugely impactful, busted a lot of the benchmarks at the time, and yeah, it became the sort of standard model that we use nowadays. That was for language. As I mentioned, you can have a decoder part of the model, and the GPT series of models use only the decoder. Some language models only use the encoder, for example, BERT, and some models are encoder-decoder models like a T5. And kind of importantly is that this transformer model spilled over into a bunch of other areas like computer vision. And so in 2020 was one of the first times that a transformer model was successfully applied to visual problems. And the way you apply it to visual problems is by basically taking your image, creating patches of it, patchifying your image, projecting each of the patches into these vectors, applying your position embeddings, and then just running a transformer encoder on it, and then getting out the, like for example, getting out the output feature vectors, and then either mean pool summing them and applying some small MLPs to do the task that you want it to do. Some people have tried applying a transformer on the raw pixels themselves, but then that's like quite a long sequence length, and oftentimes occupies too much memory. So this is one of the reasons why they do this patchification process in order to reduce the memory footprint on the GPU. And so yeah, this basically, the key breakthrough was to know how to tokenize or cut it into patches to apply the transformer to the vision domain. And so this has also been applied for audio as well. For example, the Whisper model that goes from speech to text. And also transformers have been applied for reinforcement learning to model your entire like reward state action sequence as a basically one big sequence that you learn. Great. And so you can apply this for basically anything that you encode as well. So anything that you can encode, you can encode as vectors. You can apply a transformer. And you can also, in the generation process, in the decoding process, anything you can discretize. So for example, you can discretize bounding boxes or segmentation masks. You can also use a transformer to generate these as well. Great. And so there's also a question about more efficient alternatives. And there's like a bajillion alternatives to more efficient attention formulations. And there's great survey papers about this and ways to basically categorize the different flavors of these attention alternatives. Whether, I think one big one that is, and each of these different alternatives has basically this trade-off between how much it basically improves the memory footprint and speed versus the actual downstream performance on the task, your long-range arena score. And basically you can choose basically what sort of like trade-off you want for your particular application. I'd say I'd actually single out one big attention optimization that is very commonly used, including with a lot of like the DeepSeek model series, I think uses this, and the Gemma model series uses this, which is basically sliding window attention. So basically, instead of paying attention to the whole sequence, you basically have local attention across only like a subset of the sequence. That way, for example, the stat is only attending to the 3 words before it, and similarly, and basically like a little window of 3 tokens around it. And this basically windowed attention is really common in vision and language. And finally, I think the last thing in literally the last minute is that we talked about in textbooks and a lot of sources online talk about multi-head attention, but this is not really used that frequently in modern day transformer implementations. There's a lot of different variants on this. So for example, what I described in the vanilla formulation is basically you have your queries, you dot product with the keys, and then get the attention weights, and then use that as the weighted sum of your value vectors. But you can start playing around with this a little bit by having like multiple sets of keys, use the same shared set of, multiple sets of queries, use the same shared set of keys and the same shared set of values, or just have a lot of sets of keys, just use a single basically a single head, or basically a single set of keys and a single set of values that's shared among a bunch of sets of queries. And the DeepSeek series uses, because as I mentioned, you cache your keys and values often, and this results in a big memory footprint. Oftentimes there's ways that people use to compress your keys and values by projecting them into lower dimensions, and this is what they call as multi-head latent attention. Basically, instead of using the raw keys and values, you basically project them using a low rank matrix into lower dimensionality, and this reduces the footprint of your KV cache. Great. That's like a super speedy run through transformers, and we're sort of exactly on time. Thank you for your attention, and that's it.